Hello and welcome to Unit 4 Math of Chem, Lecture C. Today we're going to talk about percents and how we use percent and mole concepts to calculate empirical formulas and molecular formulas. Okay, stoichiometry is the study of all of the math that we do in chemistry. So it's just basically math of chem and anything that has to do with our formulas and equations. So we're going to start with percent. Percent I always just define as part over whole times 100. So if you want to know how much of something, what portion of the whole amount something is, we calculate its percent. You've been doing percents for quite a while in your math class, so it shouldn't be anything new to you. We will do percent composition, and when they talk about that, they're usually talking about a compound's formula, and we start with its formula mass. So remember that gram formula mass is when we add up all of the pieces in the compound and their atomic masses off of the periodic table. So if we're doing the percent by mass of oxygen and water, your first step would be to find water's gram formula mass. So 2 hydrogens and 1 oxygen. Each hydrogen has a mass of 1. Each oxygen has a mass of 16 for a total of 18. If you want to know the percent that's oxygen by mass, you take the part that's oxygen, which is 16, divided by the whole amount, multiply by 100. If we pull up the calculator then really quick, and 16 divided by 18, and we get 89%. You're going to find that a lot of the mass of most of the chemicals that we work with are taken up by oxygen. Oxygen is the most abundant element in the Earth's crust by mass because it's in so many minerals and it's such a large portion of the water. Why is percent important to us? Well, we can't, if we have a compound, look at it and count the number of hydrogen atoms and the number of oxygen atoms. But we can take a large sample, break it apart. In the case of water, they run electricity through it, and get masses of hydrogen and masses of oxygen, and then using their atomic masses, calculate how many moles were in there, or do percent by mass. We can work with the lab data then and figure out what percent by mass comes from each element, and using that we can figure out what the actual empirical formula or molecular formula of the compound is. So it helps us to identify an unknown compound using lab data. All right, we'll use percent a lot for different things throughout the year in chemistry. It's a nice, pretty straightforward math concept that you hopefully are familiar with. Quick review of empirical formula versus molecular formula. So earlier in this unit, we learned that empirical formula was the lowest term ratio of a compound's formula of what's in it. So if we have the molecular formula for pentane as C5H10, and it actually is 5 pieces of carbon with 10 pieces of hydrogen, that ratio reduces down to 1 to 2. So this would be its empirical formula. It's not how pentane really is. Pentane really has to be made with 5 carbons, but CH2 would be its empirical formula. Ionic compounds already are in lowest terms, so their molecular and empirical formulas are the same. Why this matters to us in lab is because sometimes we can use machines to figure out what the molecular mass of something is. We can break the compound down and get this ratio by mass to find out an empirical formula, and then we can use those 2 pieces of information to figure out what its actual formula is. So we can figure out which type of compound we have. All right, so the first thing that you would do is find the mass of its empirical formula. So if we look at this first example and we have an empirical formula of C2H3, there's 2 carbons and 3 hydrogens. Each carbon has a mass of 12. Each hydrogen has a mass of 1. So the empirical formula has a gram formula mass of 27. What this means is every compound that has C2H3 for its empirical formula. So, for example, C2H3 or C4H6 or C6 H9. They all are going to have masses that are multiples of 27. So if we then look at the question and it says we have a molecular mass of 54, step 2 says divide the molecular mass by the empirical formula, or the empirical mass. So if it has a molecular mass of 54 and we divide that by 27, we find that we have 2 sets or 2 units. This multiplies by the ratios, because if I have 2 of these C2H3 units, so that I get a total mass of 54, C4H6 would be my molecular formula. Of course, you could add them together. There's only 2 sets, so that's not a big deal. But really what you would usually do, especially if this number is bigger than 2, is you multiply it through. So C2 becomes C4 and H3 becomes H6. Okay, so let's look at the next example and try that again. So we have a compound with a molecular mass of 70, and the empirical formula is CH2. So we're going to have sets of CH2s. 1 carbon, 2 hydrogens. Each carbon has a mass of 12. Each hydrogen has a mass of 1. My empirical formula is going to be in sets of 14. So remember, every compound that has the empirical formula CH2 is going to have a molecular mass that's a multiple of 14. So we're going to take the molecular mass of 70 and divide it by 14 to see how many sets, how many units of that we have. So 70 divided by 14 gives us 5. So I have 5 sets, and I just multiply the subscripts through. So CH2, and I multiply that through by 5, gives me C5H10, and that would be my molecular formula. All right, that's great if you know what the empirical formula is, but how do we find the empirical formula in lab? Where do they get that number from? Well, I said earlier that we can take something like water and run electricity through it and break it apart into its hydrogen and oxygen components. Then we can find the mass of those things, and using the Gram formula mass, we can get the mole ratio, and that's where we get this 2-to-1 mole ratio. So we can take masses and do our percent composition, and what you're going to do is pretend you have 100 grams. So if I know that a compound is 40% sulfur by mass, if I had 100 grams of my compound, I would have 40 grams of sulfur. And if the other 60% is oxygen by mass, if I had 100 grams, I would have 60 grams of oxygen. But we know that the subscripts in here, the subscripts are a mole ratio. So the first thing we're going to do is convert all of these into moles. So to do that, you need to find the atomic mass of sulfur and oxygen. So sulfur is 32 and oxygen is 16 over here in group 16. We've used them before. So if sulfur is every 1 mole is 32 grams, and oxygen every 1 mole is 16 grams, we're going to divide 40 divided by 32 gives me 1.25 moles, and then 60 divided by 16 for the oxygen gives me 3.75 moles, and that's my mole ratio. But whenever we see a formula, no matter what the compound is, this is always a whole number mole ratio. We're not going to use fractions. So when you have these decimals and you want to get the lowest whole number ratio, we're going to do step 2. Find the smallest number of moles, divide all of them by that number. So if I divide these both by 1.25, I end up with a 1 to 3 ratio. So there's my whole number ratio, and those become my subscripts. So this compound would have the empirical formula of SO3. Okay, and it's that easy, so we'll do one more example. If I have a compound where oxygen is 53.3%, we're going to pretend it's 53.3 grams, and nitrogen is 46.7%, so we're going to pretend that's 46.7 grams. We use the periodic table. Oxygen is 16. Right next to oxygen is nitrogen at 14. So we're going to multiply this by every 1 mole is 16 grams. And the nitrogen, every 1 mole is 14 grams. And I'm not doing that one in my head, so 53.3 divided by 16 gives us this horrible number, 3.33125. And for the nitrogen, 46.7 divided by 14 gives us 3.33571, etc., etc. And then we divide them both by the smallest, so 3.33125. This is going to be close enough to a 1 to 1. You're going to round these off as long as your decimal is like an 8 or a 9. You're going to round them off to a whole number anyways, and we have a 1 to 1 ratio. Be careful when we write this empirical formula, though. Oxygen and their charges. Let me erase my circles from a previous lecture here. When we write compounds, we have to put the positive first and the negative second. And if you look at our choices, nitrogen can be a whole bunch of positive ions, but oxygen can only be -2. So when we write this formula out, these subscripts, you're really going to write your compound as NO. The nitrogen's going to go first because he's going to be the positive oxidation state. All right, that wraps up today's lecture on to equations in Lecture D.